Okay, now this machine. Ready? Go. In the year 1912, an Austrian scientist named Victor Hess went up in a balloon with 3 ion detector instruments on board. His purpose was to prove that the Earth was a source of ions seeping up out of the ground, and of course they should diminish as he rose higher and higher. But instead, he discovered that the ionization rate was increasing as he went up. And when he got to the top of his climb, 17,000 feet, the rate of ionization was 4 times greater than he had measured back on the ground. And so Victor Hess had just discovered cosmic rays, and for that discovery he received a Nobel Prize. Unfortunately, the newly discovered phenomena acquired the name cosmic rays before its real nature was discovered, and the name cosmic rays stuck. However, they're not rays, not like X-rays or rays of sunshine. Cosmic ray is a stream of particles, mostly protons, but wait till I get this fixed here. Also nuclei of hydrogen, helium, including neutrons, of course, very rarely even some heavier nuclei. Furthermore, the cosmic rays we detect here on the surface of planet Earth are a byproduct classified as secondary particles. They originate when the primary particles were from somewhere out there in outer space, when they collide with ions and molecules up in the atmosphere, and they trigger a cascade of secondary particles that are called a cosmic ray shower. The primary particles impart their energy to the secondaries, and they continue in much the same direction as the primaries, and with their share of the primary energy. Now, cosmic ray showers come in a wide range of energy. The frequency of occurrence diminishes rapidly as the energy increases. Those in the highest range of energy occur only about 1 particle per square kilometer per year, and at the bottom end of the energy scale, the rate can be as high as 10,000 per square meter per minute. Okay. In this business, energy is not measured in joules or ergs. It's measured in electron volts. An electron volt is the energy acquired by an electron in traveling through 1 volt, a gradient of 1 volt. The highest cosmic ray energies are up in the 10 to the 20th electron volts. That's 100, no, that's wrong. That should be 10 to the 18th. No, that's right. That's 100 billion electron volts. A whopping pack of energy for those tiny little particles. And it's 100 million times the greater than the energy that any man-made particle accelerator can ever achieve. And whereas the source of cosmic rays with energies below, say, 10 to the 18th volt, billion that is well known, such as supernova in our galaxy or the sun, especially during sunspot activity, the source of the ultra-high energy cosmic ray showers has until very recently been a complete mystery. although it has been the subject of much speculation and conjecture. And for example, to quote from one article, such energies are so extreme that they could arise only in the most violent places in the universe. Quite so. But there has been no valid proof until now. And that brings me to the main point in giving this talk. Oh, in just a second. Yeah, sure, anytime. Number one. The task of collecting a useful quantity of extremely rare, ultra-high energy cosmic ray particles within a workable time requires a very, very large array. There are, or there has been, as many as 4 such arrays in the world. The Pierre Auger array in Argentina is by far the largest and best equipped. A consortium of 330 scientists and 32 organizations has recently built and put into operation in January 2004 the Cosmic Ray Observatory, named after Pierre Auger, a pioneer in the study of cosmic rays. Okay, Chris, you got it? Is it here? Oh, there it is. Okay. An array of 1,600 cosmic ray detectors on the ground covers an area of 30,000 square kilometers. Each detector has a large tank of water in which the particles are captured, and the water is treated chemically to cause the particles to emit a kind of radiation called Cherenkov radiation, which provides a measure of the number of particles and their energy. And around the perimeter of the array, there's 24 telescopes pointing inwards. And next page. They observe and measure the streaks of fluorescent light. I guess the next one.
Where?
Yeah, there it is. Generated by a cosmic ray shower at night. The information from 2 or more telescopes will reveal the azimuth and slope of the incoming particles, and the intensity of fluorescence will provide a measure of the energy, as well as will the Cherenkov radiation in the tanks. The detecting tanks on the surface and the fluorescent detecting scopes are complementary, and they provide cross-checks and redundancy in the measurement of cosmic ray shower parameters. The report given in Science magazine last November 9th tells of the Auger array collecting 1 million cosmic ray events since January 2004. Of that million, only 80 had energies over 40 exa-electron volts, and an exa-electron volt is 10 to the 18th electron volts. That's a billion. Only 27 of those showers had energies more than 57 exa-electron volts. And of those 27 events, 12 were found to originate within 30 degrees of, and I quote here, 30 degrees of active galactic nuclei, or AGNs. By my own count, there were another 10 events that were within 4 degrees of these AGNs, or as they're better known, black holes or quasars. Now, I must explain, active galactic nuclei, or AGNs, are galaxies with central black holes. There's a catalog with a list of all the known active galactic nuclei compiled by Veron Seti and Veron and published by Astronomy and Astrophysics. The 12th edition of the catalog contains 694 active galaxies at distances smaller than 300 million light years. At greater distances, the catalog is increasingly incomplete, but that's irrelevant here. This diagram shows how well their calculated sources coincide with the AGNs that are listed in the catalog. Is this the?
Do you want to change the slide?
I need, oh, here it is, okay.
It's just that top button.
Yeah.
Okay.
Okay. Now,
Next.
next,
There it is there, Weldon.
yeah, oh, yeah, there, whoops, caught here. Okay, well, yeah, here's a group, each ring here is the position that was calculated from the observed, and then.
I'll just hold the microphone for you. What?
Oh, sorry.
Does it?
Yeah, and all of these little asterisks, they're supposed to be red, but anyway,
Tim, you got that handheld up?
You have it.
Okay.
each of these little asterisks is one of the AGNs, or black holes, in the catalog. And of course, the thing to see is how they coincide with these rings that are the calculated positions. Well, there's 1, 2, 3, 4 calculated positions. This one here has 4 or 5 AGNs right around the perimeter. This one has one AGN where the 2 rings overlap. There's 3 coincidences here. This
Switch the other way.
one here has AGNs coinciding with that.
We'll just check the microphone there, Weldon. Sorry to interrupt. There it is.
Okay, you'll have to get that fairly close to your.
Hold it a little bit closer to your mouth.
Okay. Everybody hear me?
Okay.
Perfect for karaoke.
The most impressive results are right along this nice big cluster along here. There are, golly, I forget, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's about 15 catalog positions, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 calculated positions there. There's more bullseyes right here. There's one calculated position with a quasar right smack in the middle. This group over here also has a nice coincidence.
All right. You going to stay on this mic now?
Yeah,
Okay.
I think so.
Perfect.
Oh, yeah. Now, in the middle of this cluster I was talking about.
Can you do it from this mic? Stand.
Yeah, I think so. In the middle of this cluster here, I don't know if you can see it from back there, there's a white dot. Yeah?
Yeah.
Good. Okay, that marks the location of the galaxy Centaurus A with a capital A. And it's the only galaxy or quasar or black hole that's even identified in anywhere in this article that appeared in Science. Yeah. Okay, now the The galaxy Centaurus A is in the Centaurus constellation, of course, which is in the southern celestial hemisphere. So what's it doing there in the northern hemisphere? Well, you might well ask. The explanation is that figure 2, this figure here, is not in our conventional astral coordinates, RA and declination. It's in galactic coordinates, where the galactic equator is in parallel with the central plane of the Milky Way. Therefore, the galactic poles are tilted and displaced 63 degrees from our geographic north and south poles. So, in order to put Centaurus A in a more familiar setting, we can switch to the next one now. I took this, yeah, there we are. I got this map from our observer's handbook, all sky map. It's the May all sky map, and I also got the position of Centaurus A from another page on the whoops.
You might want to just stay by the microphone.
Yeah.
It might be easier.
Yeah.
Yeah, I got these wires in the way.
Anyway, so whoops, we're pushing the wrong button. Centaurus A, can you see the little dot there?
Yeah.
I plotted it on this all sky map from the handbook. There's where Centaurus is, right there. And that cluster that it's in, whoops, something's gone wrong. That cluster that it's in just goes down this way, and the other smaller cluster is up in this direction here. So, and there's the equator. So you can see Centaurus A is well to the south, and we'll never see it here in Ottawa. However, the Auger consortium, the people that are running the observatory here, they're planning to set up another cosmic ray observatory, even larger than the one in Argentina, somewhere in the northern hemisphere, possibly in Colorado. And together with Argentina, they should have complete coverage of the sky. Now, I have two pictures of Centaurus A.
There we go.
Ah, there it is, the whole thing. And the center is certainly shrouded in hell and brimstone. And now we can have a closer look at this. There we are looking right at the nucleus. Well, the nucleus is a black hole that's buried deep under all of that violent activity. Anyway, it certainly looks like a violent environment, and down deep in there is a black hole that sucks in everything that comes within, well, gets too close. And so makes you wonder, how come it then is it ejecting small particles, atomic particles? Isn't that typical of astronomical research? Every mystery that's solved just reveals another mystery. There's just one other item I should mention, and it involves the Big Bang and the residual cosmic microwave background. Three physicists named Grayson, Zatspin, and Kuzman theorized that ultra-high energy cosmic rays would interact with the weak 2.7 degree Kelvin cosmic microwave background, and they'd lose their significant energy if they had to travel beyond 600 million light years. And this is known as the GZK effect. GZK is the initials of the three authors of the theory. The Science article says that the data on the highest energy cosmic rays confirms this GZK theory. But the article does an obscure job of explaining how. I think their observations show a rather abrupt cutoff in energy among the showers that don't coincide with anything. And that, folks, is the end.
Thank you, Willie.
Oh, by the way, I have made a few copies of the article that appeared in Science magazine back last November. So if you're interested, just come see me. You can have a copy.
Sweet. That's great. Thank you, Willie.